Imagine a void, not just empty space, but a true nothingness. No light, no darkness, no up, no down. It's a concept that's hard to grasp, the absence of everything we know. But from this void, our universe was born. How? That's a question that has puzzled humans for millennia. But thanks to science, we're starting to get some answers. Our journey begins before time itself, before the familiar laws of physics even existed. It's a realm where our everyday intuition breaks down, and we need to turn to the language of mathematics to guide us. Don't worry, we'll translate the complex equations into stunning visuals. Think of it like a cosmic light show, where each spark and swirl represents a fundamental force shaping reality. This journey isn't just about stars and galaxies, it's about the very fabric of existence. We'll explore the mind-bending concepts of quantum mechanics and general relativity, where particles can be in multiple places at once, and gravity warps the very fabric of space and time. We'll dive into the heart of black holes, where the laws of physics as we know them break down. We'll uncover the secrets of dark matter and dark energy, the mysterious forces that make up the vast majority of the universe. And we'll grapple with the possibility of other universes, perhaps infinite in number, each with its own set of physical laws. Are you ready? Then buckle up, because we're about to embark on an epic adventure through dimensions, through quantum realms, to witness the birth of the universe. In the beginning, there was the singularity. Now, a singularity isn't a place you can visit. It's more of a concept, a point in space-time where our understanding of physics collapses. Imagine all the matter and energy of the universe, everything we can see and can't, squeezed into an infinitesimally small point. This point, this singularity, wasn't just tiny. It was also incredibly hot and dense. Think of a star 1 billion times more massive than our sun, compressed to the size of an atom. That's the kind of energy we are talking about. And within this singularity, all the forces of nature, gravity, electromagnetism, the strong and weak nuclear forces were unified. Then something incredible happened, something we call the Big Bang. But forget the image of an explosion. It's more accurate to think of it as an expansion. Space itself began to inflate, stretching faster than the speed of light. And as it expanded, it cooled, allowing energy to convert into matter according to Einstein's famous equation, HMC2. From this primordial soup of energy, the first particles emerged: quarks, leptons, bosons. These particles, the building blocks of everything we see around us, interacted with each other, forming protons, neutrons, and eventually the first atoms. And so began the epic story of our universe, a story written in the language of mathematics, a story we're only just beginning to understand. We've talked about the singularity, that point of infinite density and potential. But how do we even begin to describe such a thing? How do we talk about a realm where time and space as we know them didn't exist? This is where mathematics, the language of the universe, comes in. It's not just a tool for calculation, it's the key to understanding the fundamental fabric of reality. Just as musical notes arrange themselves into symphonies, mathematical equations orchestrate the cosmic dance of particles and forces. Imagine a painter with a palette of colors, each color representing a different aspect of the universe. Algebra, geometry, and trigonometry are like the painter's brushes, each one allowing us to paint a different aspect of the cosmic canvas. With algebra, we can express the relationships between energy, matter, and the forces that govern them. It's a language of symbols and equations, a way to quantify the universe's hidden order. Geometry, on the other hand, allows us to visualize the shape of the universe, not just in the 3 dimensions we experience daily, but in the mind-bending realm of higher dimensions. Imagine a universe folded in on itself, where different points in space are connected in ways we can barely comprehend. That's the kind of geometry we're dealing with when we talk about the very early universe. And then There's trigonometry, the mathematics of circles and waves. It might seem strange to think of circles and waves when we're talking about the birth of the universe. But remember, everything in the universe vibrates, oscillates, and interacts in rhythmic patterns. Trigonometry helps us understand these patterns, these cosmic dances that give rise to the structures we see in the universe today. Let's start with algebra. Imagine the early universe as a vast churning sea of energy. This energy wasn't uniform, it existed in different states, different quantum fields, each with its own unique properties. Algebra allows us to assign symbols to these fields, to quantify their energy levels, and to describe how they interact with each other. Think of the equation E=mc2. It's not just a random assortment of letters, it's a profound statement about the relationship between energy and mass, connected by the speed of light squared. This simple equation tells us that energy and mass are interchangeable, two sides of the same cosmic coin. Now, imagine a more complex equation, one that describes the interactions between different quantum fields in the early universe. Each term in the equation, each symbol represents a different aspect of this cosmic dance. The strength of the forces, the types of particles involved, the energy levels at play. Don't worry if it seems overwhelming. The beauty of mathematics is that it allows us to break down complex phenomena into smaller, more manageable pieces. By understanding the individual terms and how they relate to each other, we can begin to grasp the bigger picture, the grand symphony of the early universe. But algebra alone can't paint the whole picture. We need geometry to visualize the stage on which this cosmic drama unfolds. Remember the singularity, that point of infinite density? Now imagine that point expanding, not just in the three dimensions we can perceive, but in dimensions beyond our comprehension. String theory, a branch of theoretical physics, suggests that the universe might have as many as 11 dimensions. These extra dimensions, curled up and hidden from our perception, could hold the key to understanding the universe's most fundamental forces, including gravity. Imagine a garden hose viewed from a distance. It appears as a one-dimensional line, but as you get closer, you see that it has a second dimension, a circumference. String theory suggests that our universe might be similar, with extra dimensions curled up so tightly that we can't perceive them directly. These extra dimensions aren't just a mathematical trick, they could explain some of the universe's biggest mysteries, like why gravity is so much weaker than the other fundamental forces. It's like trying to fit a square peg into a round hole. Gravity might be leaking into these extra dimensions, making it appear weaker in our three-dimensional world. We've used algebra to describe the players in our cosmic drama and geometry to visualize the stage. Now we need a way to understand the unfolding action, the dynamic evolution of the universe from that initial singularity. Enter calculus, a branch of mathematics that deals with change and motion. It might seem strange to think of math as a tool for understanding something as dynamic and ever-changing as the universe, but that's precisely what calculus allows us to do. Think of a rocket launching into space. At every moment, its velocity is changing, its trajectory adjusting based on a complex interplay of forces: gravity, thrust, air resistance. Calculus gives us the tools to describe these changes, to calculate the rocket's position and velocity at any given moment. Now, imagine applying those same principles to the universe itself. The Big Bang wasn't a static event. It was the beginning of an ongoing expansion, a cosmic stretching that continues to this day. Calculus allows us to model this expansion, to track the changing distances between galaxies over billions of years. But it's not just about large-scale movements. Calculus also helps us understand the intricate dance of particles in the early universe, the formation of the first atoms, the birth of stars and galaxies. It's a language that speaks to the dynamic, ever-changing nature of the cosmos itself. One of the key concepts in calculus is the integral. Imagine you're trying to calculate the area of a circle. You could try to approximate it with squares, but you'd always be a little bit off. The integral allows us to calculate the area precisely by summing up an infinite number of infinitesimally small slices. In cosmology, integrals help us describe the evolution of the universe over time. Remember that the universe isn't just expanding, it's also filled with matter and energy that interact gravitationally. These interactions influence the rate of expansion, making it speed up or slow down over time. Integrals allow us to take all of these factors into account to calculate the universe's size and expansion rate at any point in its history. They're like time machines, allowing us to rewind the cosmic clock to those earliest moments after the Big Bang, or to fast forward billions of years to see the universe's ultimate fate. And here's where things get really interesting. By studying the universe's expansion history, we've discovered that it's not just expanding, it's accelerating. Something we call dark energy is pushing the universe apart, counteracting the pull of gravity. It's one of the biggest mysteries in modern cosmology, and integrals are our key to unraveling it. Section 3. Surfing the waves of space-time. Calculus also helps us understand the nature of space-time itself. Einstein's theory of general relativity tells us that gravity isn't a force acting at a distance, but rather a curvature of space-time caused by the presence of mass and energy. Imagine a bowling ball placed on a trampoline. It creates a dip, curvature, in the fabric of the trampoline. Similarly, massive objects like stars and galaxies create curvatures in space-time. These curvatures aren't just static dips. They can ripple and propagate like waves, carrying energy and information across the universe. We call these ripples gravitational waves. Calculus gives us the tools to describe these waves, to calculate their amplitude, frequency, and how they interact with matter. It's like listening to the universe breathe, to hear the echoes of cosmic events like colliding black holes or the Big Bang itself. In recent years, scientists have been able to detect gravitational waves directly, confirming Einstein's predictions and opening up a whole new window into the universe. With each new detection, we're learning more about the nature of gravity, the behavior of black holes, and the earliest moments of the universe's history. And at the heart of it all, guiding our understanding, is the language of calculus. Section 1. The Quantum Realm, a Sea of Possibilities. So far, our journey has taken us from the vast scales of cosmic expansion to the mind-bending curvatures of space-time. But to truly understand the birth of the universe, we need to delve even deeper into the realm of the very small, where the classical laws of physics break down and a new set of rules takes over, the bizarre and counterintuitive world of quantum mechanics. In the quantum realm, particles don't behave like tiny billiard balls. They're more like fuzzy waves spread out over space, their properties governed by probability rather than certainty. Imagine a coin spinning in the air. You can't say for sure whether it will land heads or tails until it comes to rest. Similarly, in the quantum world, we can only talk about the probability of finding a particle in a particular location or with a particular energy. It's like trying to track a school of fish darting through the ocean. You can see the general movement, but the individual fish are constantly shifting and changing direction. This inherent uncertainty isn't a limitation of our instruments. It's a fundamental property of the quantum world. It means that the universe at its most fundamental level is not deterministic, but probabilistic, a sea of possibilities constantly in flux. And from this sea of possibilities, our universe, with all its order and complexity, emerged. Section 2. Quantum Electrodynamics, Dancing with Light. One of the most successful theories in all of physics is quantum electrodynamics, or QED, which describes the interaction between light and matter. Light, as we know it, is made up of particles called photons, massless packets of energy that travel at the speed of light. But in the quantum world, photons don't just carry energy, they also mediate forces. Imagine two electrons, both negatively charged and therefore repelling each other. In classical physics, we'd say that they exert an electrostatic force on each other. But in QED, this force is mediated by the exchange of virtual photons. It's like two people on ice skates, throwing a ball back and forth. Each throw pushes them further apart. These virtual photons are like fleeting ghosts popping in and out of existence, carrying momentum and energy but not directly observable. Yet they have a real measurable effect on the world around us. QED has been incredibly successful in explaining everything from the behavior of atoms to the properties of light itself. In the early universe, QED played a crucial role in shaping the cosmos as we know it. It governed the interactions between charged particles, influencing the formation of the first atoms and the eventual emergence of stars and galaxies. It's a testament to the power of quantum mechanics that a theory based on probability and uncertainty can explain the universe with such incredible precision. From chaos to cosmos, the emergence of structure. So we have this picture of the early universe, a hot, dense soup of particles governed by the probabilistic laws of quantum mechanics. It seems chaotic, random, and yet from this chaos, order emerged. How did this happen? How did the universe go from a formless sea of particles to the structured cosmos we see today? One of the key factors was the cooling of the universe as it expanded. As the universe cooled, the energy of the particles decreased and they began to clump together under the influence of gravity. Imagine steam condensing into water droplets. As the temperature drops, the water molecules slow down and stick together. Similarly, in the early universe, gravity acted as a sculptor, gradually shaping the random distribution of matter into clumps and filaments. These clumps grew larger and denser over time, eventually collapsing under their own gravity to form the first stars and galaxies. But gravity alone can't explain the large-scale structure of the universe we see today. There's another, more mysterious player at work: dark matter. This invisible substance, which makes up the vast majority of the universe's mass, doesn't interact with light, but its gravitational influence is undeniable. It's like an invisible scaffolding, guiding the distribution of visible matter and shaping the cosmic web of galaxies we observe today. The arrow of time, a one-way street. We've explored the quantum realm, the dance of light and matter, and the emergence of structure in the universe. But there's another fundamental concept we need to address: time. In our everyday experience, time flows in one direction, from past to present to future. We remember the past but not the future. We age and experience events in a linear sequence. But why is this so? Why does time have an arrow? In the grand scheme of the universe, the arrow of time is intimately linked to a concept called entropy. In simple terms, entropy is a measure of disorder or randomness. Think of a neat and tidy room versus a messy one. The messy room has higher entropy, more disorder. The second law of thermodynamics, one of the fundamental laws of physics, states that the total entropy of a closed system can only increase over time. In other words, things tend to get messier, not neater, on their own. You have to put in energy, do work to clean up your room or organize your desk. Now apply this principle to the universe as a whole. The early universe, just after the Big Bang, was in a state of very low entropy, incredibly hot, dense, and uniform. But as the universe expanded and cooled, entropy increased. Stars formed, burned out, and exploded, scattering their contents across space. Galaxies collided and merged, creating more complex structures. Entropy, the universe's messy room. Think of the universe as a giant box. At the beginning, this box was very small and contained only a few simple ingredients, all mixed evenly. This represents a state of low entropy, high order. But as the universe expanded, the box got bigger. More particles were created, and they started to interact in more complex ways. Imagine those particles as toys scattered randomly around a child's playroom. Over time, those toys don't magically arrange themselves back into their boxes. Instead, they tend to get more spread out, more disordered. That's entropy at work. In the universe, this increase in entropy manifests itself in various ways. Stars burn fuel and radiate energy into space, increasing the overall disorder. Black holes form, trapping matter and energy in their infinitely dense singularities. Galaxies move further apart as space-time expands. This doesn't mean the universe is becoming a chaotic mess. Order and complexity can arise locally, as in the formation of stars, planets, and even life itself. But these processes always come at the cost of increasing entropy elsewhere. It's like building a sandcastle on the beach. You create something ordered and beautiful, but you also disturb the sand around it, increasing the overall disorder. Section 3. Echoes of the Big Bang, the cosmic microwave background. One of the most compelling pieces of evidence for the Big Bang and the arrow of time is the cosmic microwave background radiation, often referred to as the CMB. This faint afterglow of the Big Bang permeates all of space and provides us with a snapshot of the universe as it was just 380,000 years after the Big Bang. Imagine looking up at the night sky and seeing, not stars, but a faint uniform glow in every direction. That's what the CMB is like, but it's not visible to the naked eye. We detect it using specialized telescopes that can pick up microwaves, a type of electromagnetic radiation. The CMB is incredibly smooth, with a nearly uniform temperature in all directions. This tells us that the early universe was remarkably homogeneous, with matter and energy distributed very evenly. But the CMB also contains tiny temperature fluctuations, variations of just a few parts in 100,000. These fluctuations are incredibly important because they represent the seeds of structure in the universe. They tell us that the early universe wasn't perfectly smooth. There were tiny regions where matter was slightly denser than average. These denser regions, under the influence of gravity, eventually grew into the stars, galaxies, and galaxy clusters we see today. The CMB is like a cosmic blueprint imprinted on the fabric of space-time, revealing the universe's earliest moments and foreshadowing its future evolution. Section 1. Quantum Gravity, the Final Frontier. In our exploration of the universe, we've delved into the realms of the very large and the very small, but there's one frontier that remains elusive: quantum gravity. This is the holy grail of modern physics, the theory that aims to unify general relativity, which describes gravity and the curvature of space-time, with quantum mechanics, which governs the behavior of particles on the smallest scales. Imagine trying to reconcile the smooth, continuous fabric of space-time with the chaotic, probabilistic nature of the quantum world. It's like trying to fit a square peg into a round hole. Traditional physics has struggled to bridge this gap, but promising theories like string theory and loop quantum gravity offer potential paths forward. String theory suggests that the fundamental building blocks of the universe aren't particles, but tiny vibrating strings. These strings can stretch and twist through multiple dimensions, creating the particles and forces we observe. This framework provides a way to incorporate gravity into the quantum realm, potentially leading to a unified theory. Another approach, loop quantum gravity, proposes that space-time itself has a discrete structure, made up of tiny loops woven together like a cosmic fabric. This theory suggests that on the smallest scales, space-time isn't smooth, but rather quantized, with a granular structure. Both string theory and loop quantum gravity are still in development, but they offer intriguing glimpses into the nature of quantum gravity. quantum gravity isn't just an abstract concept. It has real implications for our understanding of the universe. For example, it could help explain what happens inside black holes, where gravitational forces become so intense that they warp space-time to an extreme degree. It could also shed light on the very moment of the Big Bang where our current theories break down. As we continue to explore this final frontier, we move closer to a complete understanding of the cosmos. Section 2, Dark Matter, the Invisible Hand. While we've made great strides in understanding the universe, there are still many mysteries left to solve. One of the biggest is dark matter. This elusive substance doesn't emit, absorb, or reflect light, making it invisible to our telescopes. Yet its gravitational influence is undeniable, shaping galaxies and clusters in ways that we can observe. Imagine trying to understand a game of chess without being able to see the pieces. You could infer their presence and movements from the effects on the board, but the exact nature of the pieces would remain a mystery. That's our current situation with dark matter. We can see its effects on the motions of galaxies and the bending of light, but we can't see the dark matter itself. Dark matter makes up about 27% of the universe's mass energy content, far more than the visible matter that makes up stars, planets, and everything we can see. One of the leading candidates for dark matter is the WIMP, or Weakly Interacting Massive Particle. WIMPs are thought to interact with other matter only through gravity and the weak nuclear force, making them incredibly difficult to detect. Experiments around the world are searching for clues about dark matter. Detectors buried deep underground aim to catch the rare interactions of WIMPs with ordinary matter. Meanwhile, telescopes scan the skies for indirect evidence, such as the gamma rays that might be produced when dark matter particles annihilate each other. Despite these efforts, dark matter remains an enigma. It's like a ghostly hand, gently guiding the formation and evolution of galaxies, yet always just out of reach. Understanding dark matter is one of the biggest challenges in modern physics, and solving this mystery could revolutionize our understanding of the universe. As we push the boundaries of our understanding, we encounter the concept of the multiverse. This idea suggests that our universe is just one of many, each with its own set of physical laws and constants. It's a mind-boggling notion that challenges our perception of reality, but it's grounded in some of the most advanced theories in physics, including string theory and inflationary cosmology. Imagine our universe as a bubble floating in a vast cosmic foam with countless other bubbles, each representing a different universe. Some of these universes might be very similar to our own, while others could be drastically different, with different dimensions, particles, and forces. The mathematics behind the multiverse is deeply rooted in the theory of inflation, which proposes that the universe underwent a rapid expansion just after the Big Bang. This inflationary period could have created bubbles of space-time, each evolving into a separate universe. The equations describing this process are complex, involving integrals and differential equations that stretch the limits of our mathematical understanding. String theory also supports the idea of a multiverse. In this framework, the different ways that strings can vibrate correspond to different particles and forces. There are potentially countless ways for strings to vibrate, each corresponding to a different set of physical laws. This diversity could give rise to a multitude of universes, each with its own unique properties. The concept of the multiverse isn't just theoretical speculation, it has profound implications for our understanding of reality. It suggests that the physical constants we observe, such as the speed of light or the strength of gravity, might not be unique, but rather just one set of possibilities among many. This perspective could help explain why our universe seems so finely tuned for life. As we continue to explore these mathematical realms, we push the boundaries of what we know and venture into the unknown. The quest to understand the multiverse is a journey that challenges our imagination and expands our horizons, hinting at a reality far grander than we ever imagined. We've journeyed through vast cosmic landscapes, explored the bizarre quantum realm, and confronted the mysteries of dark matter and the multiverse. Now, let's zoom in on the building blocks of matter itself, quarks. These tiny particles, smaller than atoms, are the fundamental constituents of protons and neutrons, the very heart of matter as we know it. Imagine a universe filled with a sea of quarks, not yet confined within the familiar structures of atoms. These quarks, governed by the laws of quantum mechanics, exist in a superposition of states, their positions and properties constantly fluctuating. As the universe expands and cools, these quarks don't just passively drift apart, they interact with each other, exchanging energy and momentum, their movements influenced by the expanding space-time around them. To understand these interactions, we need to delve into the realm of quark mathematics. Think of quarks as tiny, spinning tops, each with its own unique set of properties, including charge, spin, and mass. These properties determine how quarks interact with each other and with the fundamental forces of nature. Mathematical equations, often involving complex integrals and derivatives, allow us to describe these interactions, to track the movement of quarks through space-time, and to understand how they eventually come together to form the building blocks of matter. But quarks don't just interact through gravity and electromagnetism, the forces we experience in our everyday lives. They're also bound together by a much stronger force, appropriately named the strong force. This force, described by a theory called quantum chromodynamics, or QCD, is responsible for holding quarks together within protons and neutrons. Imagine trying to pull apart two magnets that are stuck together. You have to exert a certain amount of force to overcome the magnetic attraction. The strong force is similar, but on a much, much stronger scale. It takes an immense amount of energy to separate quarks, and even then, they don't stay apart for long. QCD is a complex theory involving the exchange of particles called gluons, which mediate the strong force between quarks. These gluons act like a kind of cosmic glue, binding quarks together with incredible strength. The mathematics of QCD is intricate, involving complex equations and concepts like color charge, which describes how quarks interact through the strong force. In the early universe, QCD played a crucial role in the formation of protons and neutrons. As the universe cooled, quarks were drawn together by the strong force, overcoming their tendency to spread out due to entropy. These bound states of quarks, held together by the relentless grip of the strong force, formed the stable nuclei of atoms, setting the stage for the emergence of the elements and the eventual formation of stars and galaxies. So, from the tiniest particles to the largest cosmic structures, we see a universe governed by mathematical laws. The dance of quarks, the interactions of particles and forces, the expansion of space-time itself, all can be described, at least in part, by the language of mathematics. But this isn't a cold, sterile picture of the universe. It's a story of emergence, of complexity arising from simplicity. The same fundamental laws that govern the interactions of quarks also give rise to the diversity of elements, the formation of stars, the intricate dance of planets around those stars, and ultimately the conditions necessary for life itself to emerge. Our journey through dimensions and quantum realms has taken us to the very edge of human knowledge. We've encountered concepts that challenge our intuition, equations that stretch the limits of our understanding. And yet, with each new discovery, with each new mathematical insight, we gain a deeper appreciation for the elegance, the beauty, and the profound interconnectedness of the universe. From the tiniest quark to the largest supercluster of galaxies, We are all part of this grand cosmic story, a story written in the language of mathematics, a story that continues to unfold before our very eyes. As we continue to explore, to question, and to push the boundaries of human knowledge, we can be sure that the universe will continue to surprise us, to challenge us, and to inspire us with its boundless wonder. Our journey began with a void, an abstract concept defying imagination. Yet, from this void emerged a universe of staggering scale and complexity. We zoomed in on the infinitesimal, exploring the bizarre quantum realm where particles dance to the rhythm of probability, not certainty. We witnessed the incredible power of the strong force, binding quarks together within the hearts of atoms, the very building blocks of matter. We then shifted our perspective, expanding outwards, propelled by the relentless force of cosmic expansion. We saw how gravity, a force so familiar yet so mysterious, sculpts the universe, drawing matter together to form stars, galaxies, and vast cosmic webs. We grappled with the enigmatic presence of dark matter, its invisible hand guiding the evolution of galactic structures. From the smallest particles to the largest cosmic structures, a common thread emerges, the language of mathematics. We've seen how equations, integrals, and derivatives, far from being abstract symbols, describe the very essence of the universe. They capture the interactions of particles, the curvature of space-time, the evolution of the cosmos itself. This mathematical framework isn't just a tool for calculation, it's a lens through which we perceive the underlying order, the intricate relationships that govern the universe at every level. It reveals a symphony of scales, a harmonious interplay of forces and particles, from the quantum foam to the cosmic horizon. Our exploration of the universe's birth is far from over. The more we learn, the more we realize how much remains unknown. The quest for quantum gravity, the search for dark matter particles, the exploration of the multiverse. These are just a few of the frontiers that beckon us forward. Each new discovery, each theoretical breakthrough expands our cosmic perspective, challenging our assumptions about reality itself. We're no longer passive observers of the cosmos, we're active participants in a grand scientific endeavor, using the tools of mathematics and observation to unravel the universe's deepest secrets. As we continue this journey, we can be sure of one thing: the universe will continue to surprise us. It will challenge our intuition, push the boundaries of our imagination, and inspire us with its awe-inspiring beauty and complexity. The birth of the universe, once shrouded in mystery, is now a story that we can begin to tell, a story written in the language of mathematics, a story that continues to unfold before our very eyes. So, let us embrace the unknown, celebrate the mysteries that still lie hidden, and continue to explore, to question, and to marvel at the universe we are so fortunate to inhabit. For in the words of Carl Sagan, somewhere, something incredible is waiting to be known.